Hi everyone! Today we're going to discuss trees and forests. This is a continuation of our discussions on fundamentals of graph. So if you are ready, halina't matuto. So what is a tree? A connected graph that has no cycle is a tree. A forest is a graph whose components are trees. So any graph that contains no cycle is defined as a tree. This is an example of a tree with four vertices and three edges. This is another example of a tree, which is also a pot. So a pot is an example of a tree. So for as long as a graph does not contain any cycle, then by definition, it is a tree. Although the third example looks like a dog, since it has no cycle, then it can also be considered as a tree. Our fourth example more or less illustrate a more general structure of a tree. Somehow we can think of this as having a root, a stem, and its leaves. A graph whose components are all trees is called a forest. So this is an example of a forest with four trees. The vertices of degree 1 and the edges incident to it in a tree are called its leaves. In our first example, these three are the leaves of our tree. For a pot, the leaves are the end points. So those are our leaves. In our third example, we have 1, 2, 3, 4, 5, 6 leaves. In our fourth example, although if we try to imagine it as a tree, this looks like its roots, but technically speaking, these three are leaves as well. Together with these branches, so those are the leaves of our trees. Now, here is our theorem on how we can identify whether a graph is a tree or not. So let E be a graph with n vertices. The following are equivalent statements. T is a tree if and only if T contains no cycle and has exactly n minus 1 edges. So by definition, a tree contains no cycle. Additionally, if it is a tree, then it has exactly n minus 1 edges. Looking at our example, this tree here, the first one, has four vertices and exactly 1, 2, 3, 4 minus 1 edges. For our second example, which is a pot of length 4, this has 5 vertices. So there are exactly 5 minus 1, which is 4 edges. On our third example, which looks like a dog, this has 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. And it has 1, 2, 3, 4, 5, 6, 7, 8, which is exactly 9 minus 1 edges. So in any tree, there's always n minus 1 edges. Next, it is a tree if T is connected and has n minus 1 edges. So if it is a connected graph with n minus 1 edges, then it is a tree. T is minimally connected. That is, each edge is a bridge. So if you delete any edge in a tree, then you make your tree disconnected. So that's what it means by minimally connected. Any deletion of edges in any tree then your tree will become disconnected. So that means any edge in a tree is a bridge or a cut edge. Any two vertices of T is connected by exactly one path. So if we look at our example, and if we take any two vertices, let's say we take this vertex and another vertex. So if we find a path connecting these two vertices, then there is exactly one path. So no other path can connect these two vertices except for that specific path. Any two vertices for that matter. For example, let's take another two vertices. Let's take this vertex here and a vertex on its root. So to connect, we need to take this path. But as you can see, there's no other path wherein these two vertices are connected but this path alone. So any two vertices are connected by a unique path. Exactly one path. And finally, T is maximally acyclic. That is, T contains no cycle. Of course, that's by definition. But the addition of any new edge create exactly one cycle. So kung magdadagdag daw tayo ng isa pang edge, then makakikreate tayo ng exactly one cycle dun sa tree natin. For example, let's take again our tree. So as we can see, this tree contains no cycle. But if we connect any two non-connected vertices, then we will create exactly one cycle. For example, if I choose this vertex here and this vertex here, if I connect them, then they're exactly one cycle produced, no other. Let's take another example. So by connecting, let's say, this edge here, and I connect it to vertex rather, and I connect it to this vertex here. So if I create an edge connecting these two, then I create this cycle plus the additional connection. Every time you add one edge, you create a cycle. So it's maximally acyclic. So it contains no cycle, but any addition of new edge will no longer make it acyclic. So acyclic means it has no cycle. So it's maximal already. So what we will do now is we will prove this theorem. Okay? So how do we prove equivalent statements? To prove by conditional statements, for example, we have P if and only if Q. We need to show that P implies Q and Q implies P. Now, what we want here are six different statements which we say to be equivalent. So, to prove that these six statements are equivalent, what we can do is we can show that 1 implies 2. And then once we've shown that 1 implies 2, we will show that 2 implies 3. And then we will show that 3 implies 4 and that 4 implies 5. 5 implies 6 and then eventually we will show that 6 implies 1. So once you've shown these 6 implications, this will already mean that each of the statements are equivalent. For example, 2 and 4 are equivalent statements. By transitivity, 2 implies 3 and 3 implies 4. So that would imply that 2 implies 4. But at the same time, since 4 implies 5, 5 implies 6, 6 implies 1, 1 implies 2. By transitivity, it also means that 4 implies 2. So since 2 implies 4 and 4 implies 2, then 2 and 4 are equivalent statements. Using that same concept of transitivity, then it means that each of these statements are equivalent. So if T is a 3, then any of the other 5 statements will also be true. So we now proceed by proving these 6 implications to show that the 6 statements are equivalent. So first, let's prove 1 implies 2. We first assume that T is a tree, and then we show that T contains no cycle and has exactly n minus 1 edges. By definition, a tree contains no cycle. So we're already done with this part. It is now left to show that if a tree has n vertices, then it must have exactly n minus 1 edges. And we will do this by induction. Consider the proposition T is a tree with n vertices, then T has n minus 1 edges. Observe that for n equals 1, a tree with only one vertex obviously has 0 edge. Therefore, P of 1 is true. Now, for n equals 2, a graph with two vertices and exactly one edge is a tree. Therefore, P of 2 is true. Now, let's assume that P of 1, P of 2, and so on, up to P of n are true. In other words, any tree with k vertices where k is less than or equal to n has exactly k minus 1 edges. So what we want to show is that P of n plus 1 is also true. Suppose T is a tree with n plus 1 vertices. Since T contains no cycle, a removal of an edge will disconnect T. To illustrate, let's say we have this T and we remove an edge of the graph. So there's a deleted edge here. Since the edge is not contained in a cycle, we are sure that this edge will disconnect our graph. So now we have two components of the graph. So let's say we have this component 1 and component 2. Let's say that this component has L vertices and this component has M vertices. Since the total number of vertices in T is n plus 1, then that would mean that L plus M is equal to n plus 1. Likewise, we are sure that L is less than or equal to n and M is also less than or equal to n. At the very most, the number of vertices in one of its components will be n. And that will happen if you delete the edge on its leaf, like this one. So that will separate your graph into two components where one of the component has only one vertex and the rest has n vertices. But well, in general, we have L and M vertices. Since the original graph contains no cycle, then the resulting components obviously contains no cycle as well. By our hypothesis, so the first component has L minus 1 edges, and the second component has M minus 1 edges. So all in all, T has, from the first component, L minus 1 edges, from the second component, M minus 1 edges, and the deleted edge, plus 1. Or that's equal to L plus M minus 1. But since L plus M is equal to N plus 1, then E has N edges. This implies that P of N plus 1 is also true. By induction, P of n is true for all n. So that proves that a tree with n vertices has n minus 1 edges. Now let's prove 2 implies 3. Assume that T contains no cycle and has exactly n minus 1 edges. We want to show that T is connected and has n minus 1 edges. That T has n minus 1 edges is already done since it is assumed. So now, all we need to do is to show that T is connected. We want to show this by contradiction. So suppose T is disconnected. So that means T has two or more components. To illustrate, let's say that T has at least two components. Of course, in general, T may have more than two components. Now, by assumption, T contains no cycle. So each component must contain no cycle as well. So since a component is a maximally connected subgraph of T, then each component is a connected graph which contain no cycle. By the previous result, then the number of vertices in each component exceeds the number of edges by 1. So if the first component say has L edges, then L must have L plus 1 vertices. If the second component has M edges, then it has M plus 1 vertices. And this is true for all the components of T. Now, if we add all the number of vertices and the number of edges in T, this is the same as adding all the number of vertices and all the number of edges in each component. So in our illustration, if T has only two components, we see that the number of edges of T is L plus M, and the number of vertices is L plus M plus 2. That means that the total number of vertices in T exceeds the total number of edges. By how much? By at least 2. If there are only two components, then by exactly 2. But if T has more than two components, then at the very least, the number of vertices is 2 more than the number of edges. But that is a contradiction. Why? Because by assumption, T has only n minus 1 edges. So that means that the difference must be exactly 1. Then our supposition must be false. Or that means T is connected. Next, we want to show that 3 implies 4. So we assume that T is connected and has n minus 1 edges. Then we show that T is minimally connected. That is, each edge is a bridge. For this, we need to recall a certain theorem from our previous discussions about connectivity. Recall that if a group G with vertex set V and edge set E such that the number of vertices is n, the number of edges is m, and the number of component is k, then n minus k is less than or equal to m. So suppose T is connected and has n minus 1 edges. Now, if we remove an edge, this will result in a graph with n vertices and this time n minus 2 edges. Now, observe here that n minus m is less than or equal to k, or the number of components is greater than or equal to n minus m. So this resulting graph here has n vertices and n minus 2 edges. So that means that for our graph, k is greater than or equal to n minus n minus 2, which is equal to 2. So that means that the resulting graph has at least two components. And that means that this is disconnected. So every time we delete an edge, it makes our graph disconnected. That means that edge that we delete is a cut edge, or in short, a bridge. Since the deleted edge is arbitrary, that means that any edge in the graph is a bridge. Next, we show that 4 implies 5. If T is minimally connected, that is each edge is a bridge, we want to show that any two vertices of T is connected by exactly one path. If T is connected, then of course any pair of vertices is connected by at least one path. Let's say these are the two vertices, and this is a path connecting these two vertices. Now, if there is another path that connects these two vertices different from this path, say this path, then these two paths forms a cycle. Actually, this path may contain edges that are common to P. But for as long as there is an edge different from that of P, then this would be a different path. Meaning, P prime could follow the same trail as P and will be different from, say, a particular trail on P. But nevertheless, it will still contain a cycle. In any case, two distinct paths from a pair of vertices will inevitably contain a cycle. And this is a contradiction since we assume that each edge is a bridge. And of course, we already know from our previous discussion that a bridge is not contained in any cycle. And so, any two vertices in T is connected by exactly one path. So, this path, distinct from P, cannot exist. Next, we prove that 5 implies 6. We assume that any two vertices of T is connected by exactly one path, and then we show that T is maximally acyclic. So, to show that T is maximally acyclic, we need to show two things. First, that T contains no cycle, and that the addition of any new edge creates exactly one cycle. The first one is easy to show. So let's say we have a cycle in T. Then any pair of vertices in that cycle is connected by two different paths. This path and the other part of the cycle. But by assumption, any pair of vertices is connected by exactly one path. So this cannot happen. So that means T contains no cycle. Next, we want to show that if we add new edge, we produce exactly one cycle. First, it's easy to show that you will be able to create one cycle. Why is that? Suppose you have two non-adjacent vertices, U and V. We assume that U and V are not adjacent because we want to add this as a new edge. If they are already adjacent, then you didn't add any edge. So let's assume that U and V are non-adjacent vertices in our graph. By assumption, it has exactly one path that connect U and V. So let's say this is a path connecting U and V. So if you create or you add edge UV, then P plus UV obviously is a cycle. So we're already sure that once you add a new edge, you create a cycle. Now, how do we say that this is the only cycle that was created? So let's assume that there's another cycle created by introducing the edge UV. So let's say that this is a new cycle created by the edge UV, right? So that would imply that that is another path from U to V. And that will contradict our assumption that there are exactly one path that connects U to B. So that means this path is not possible. So adding the edge UV will add exactly one cycle. Finally, we want to show that 6 implies 1. That is, if T is maximally acyclic, then T is a 3. Of course, since by assumption, T is acyclic or it contains no cycle, then it suffices to show that for it to be a tree, it must be connected as well. So by assuming that it is maximally acyclic, all we need to show now is that T is connected. By definition, if it is connected and it contains no cycle, then it must be a tree. So suppose, by contradiction, that T is not connected. So suppose T is disconnected, meaning it has two or more components. So let's say we have two components. So let's say we have a component here and a component here. And we choose a vertex U here and a vertex V on the other component. Now, since these components are disjoint, then there are no edges joining U and V together, or there are no path connecting the two. Now, if we add to T an edge joining these vertices, no cycle is formed, right? Because that's the only connection between these two components. So obviously, T plus E contains no cycle. But this contradicts our assumption that every time we connect an edge, it must produce exactly one cycle. So that means before putting this E, there should have been a path connecting U and V already. So that once you add edge E, a cycle is created. But if we assume that T is disconnected, then that cannot happen. So T being disconnected must be false. Therefore, T is connected. And that completes our proof. This theorem gives us a way to characterize a tree. So whenever any of these properties are observed in a graph, then that graph is a tree. Let me recall these properties. So if T is a tree with n vertices, then T contains no cycle and has exactly n minus 1 edges. Meaning if you see a graph with no cycle and you count the number of edges and there are exactly n minus 1 edges, then that particular graph is a tree. Now, if you see a connected graph with n minus 1 edges, then that's also a tree. If a graph is minimally connected, that is every time you delete an edge, the graph becomes disconnected, then that graph is a tree. Next, any two vertices of T is connected by exactly one path. So if you see that a graph connects two different vertices with at least two different paths, then that's not a tree. And finally, T is maximally acyclic, meaning T contains no cycle, and every time you add an edge, you create a cycle. Now for a connected graph G, a subgraph T of G, which contains all the vertices of G that is also a tree, is called a spanning tree. Every connected graph has a spanning tree. This is both a minimally connected subgraph of G and also a maximally acyclic subgraph of G. Again, what do we mean by minimally connected? So, meron kang graph, connected siya, pero masasabi mo siyang minimally connected if whenever you remove an edge from this minimally connected subgraph, nagiging disconnected na siya. So, that's what we mean by a minimally connected subgraph. Or that means every edge is a bridge. On the other hand, this same minimally connected subgraph of G is also a maximally acyclic subgraph of G. Meaning, this is a subgraph of G that contains no cycle. Pero, pag nagdagdag tayo ng isa pang edge ng G, may nabubuo na tayong cycle. So that's what we mean by a maximally acyclic subgraph. Finding spanning tree of any connected graph has piqued the interest of some mathematicians. For a simple connected graph, these are the steps in generating a spanning tree for any connected graph. This follows the same concept of the tree being a minimally connected graph or a maximally acyclic subgraph. So remember that a subgraph is a spanning tree if it is a tree which contains all the vertices of the graph. So medyo madali lang namang mag-generate ng spanning tree. Remember, para makapag-create ka ng tree, dapat wala kang cycle by definition. So pag nakakita ka ng cycle sa isang graph, ang gagawin mo lang, magdi-delete ka ng edge para mawala yung cycle na yan. So just repeat this process every time na makakita ka ng cycle, mag-delete ka ng isang edge ng cycle na yan. So wala na yung cycle na yan. And then repeat this process until no cycles are left. Kung ano yung matitira, that's a spanning tree. Basta wag kang magdi-delete ng vertices, puro edge lang. And isang edge lang lagi. For every cycle, isang edge lang yung i-delete mo. So that it will remain connected. Kumbaga, ang nangyayari, meron kang cycle na nagko-connect ng mga points na to. So, what you want is to delete a path from one point U to the other para isang path lang yung matitira. Kasi sabi nga natin, di ba, ang tree dapat isa lang yung path. So, ang gagawin mo lang, i-delete mo yung edge UB para isa lang yung path papunta sa UNV. So, kung meron pang ibang cycle na na-form, i-delete mo rin yung mga cycle na makikita mo pa. Para yung matitira na lang is just a spanning tree. Let's have an example. Let's say we have this graph with 7 vertices. So let's find a spanning tree for this graph. So here's another copy of the graph. So what we're going to do is that we will identify a cycle, and then on that cycle, we will delete an edge on that cycle. Any edge for that matter. So for example, I have this cycle here. Step 2, all we need to do is to delete a specific edge, any edge. So let's say I want to delete this edge. So do that for every cycle that you can find. For instance, there is a cycle connecting these 4 vertices. So just choose any edge that you want to delete. Let's say I want to delete this edge. Then find another cycle. There is a cycle connecting these 3. So let me delete one of the edges. Next, there's a cycle here. So let me delete this edge. This is a cycle. So let me delete this edge. You can delete any edge that you want. It doesn't matter which edge you want to delete. For as long as you see a cycle, just delete an edge. These 3 forms a cycle, so let me delete an edge. Okay, there's still a cycle here. This is a cycle, so let me delete this edge. There is a cycle here, so let me delete an edge. Okay, it doesn't seem a usual cycle, but actually, this is a cycle here. These 4 vertices form a cycle. So let me delete one edge. Similarly, these 4 vertices as well form a cycle. So let me delete an edge as well. So finally, there are no more cycles. So what remains is a spanning tree. Observe that this spanning tree has 1, 2, 3, 4, 5, 6 edges. And as shown a while ago, we know that a tree with n vertices must have n minus 1 edges. So since we have 7 vertices, then the spanning tree must have 6 edges. Now, a spanning tree of a graph is not unique. You can have multiple spanning tree for the same graph. For example, let me find another spanning tree for this graph. So here's another copy of the same graph. So it actually depends on our choice of the cycle and which edge we want to delete. So that will generate a different spanning tree each time. So for example, let's say that for this triangle, I delete this edge. Now let me find another cycle. So for this, let me delete this edge. For this cycle, let me delete this edge. There is a cycle here. So let's delete this edge. There is a cycle here. So let me delete this edge. So every cycle, just delete an edge. This is a cycle. 1, 2, 3. So let's delete this edge. There's a cycle here. The 3 vertices. So let me delete this edge. I can still find a cycle here. So let me delete this edge. Now this triangle here, let me delete this edge. And this is a cycle. So let me delete an edge. This no longer contains any cycle. So what remains is a tree. So this is another spanning tree for that same graph. So again, spanning tree are not unique. So you can have multiple spanning tree for the same graph. It's just a matter of choice which particular edge you will delete until you are left with a tree. So basically what you're doing is that you're just deleting edges so that the resulting graph will remain connected until such time that it will no longer contain a cycle. So it's what we call a minimally connected subgraph. Kasi ina-avoid mo siyang ma-disconnect pero tinatanggal mo lang yung mga cycle niya. Now, pwede mo rin siyang tingnan as a maximally acyclic subgraph. So, paano naman yung criteria pag tinitingnan mo siya as a maximally acyclic subgraph? So, this time naman, mag-a-add ka ng mag-a-add ng mga edge without creating a cycle. Pabaliktad naman. So, pero same idea pa rin. Ultimately, ang i-create mo pa rin is a subgraph that contains no cycle. So, paano naman yan? Kanina, nag-start tayo sa buong graph, tapos nag-delete tayo ng edge ng cycle para mawala yung cycle. Pero nananatili pa rin siyang connected. Okay. So, that's the idea. We make a minimally connected subgraph of G. Okay. This time around, let's start with a starting vertex and then let's create a tree using the edges of the graph. So let V sub 0 be any starting vertex in G. And let T be the tree containing that vertex V sub 0. So initially, isa pa lang yung vertex ng graph natin. Tapos bubuuin natin yung subgraph containing the edges of G without any cycle. Okay? Let's get our previous graph as an example. So again, you can start with any of its vertices. And this will be our initial T. So, kumbaga, yung T natin, papalakihin natin ng papalakihin hanggang makuha natin lahat ng mga edges. So, let's say, I want to start with this initial vertex. Okay? Now, from here, what we do is, we get any of the vertices adjacent to this vertex that is not yet in T. So, at the moment, T contains only this vertex. Yan pa lang yung laman ni T. So, gagawin mo, kukunin mo yung any vertex not in T na connected kay V sub 0. So, pili ka lang ng kahit anong connected. For instance, I want this one. So, yan na yung bago mong T. So, your new T now will contain two vertices. So, your T now the vertex set for T will now contain V sub 0 and that new vertex V1. And of course, including yung edge between them. Okay? So, meron ka ng tree with two vertices. Now, repeat this process. So, pipili ka ng vertex na wala kay T pero adjacent sa any of the vertices ni T. For example, this point. Adjacent siya kay V1. So, tatawagin ko na tong V2. And then, the edge connecting V2 and V1 will now be included kay T. So, yung T natin, tatlo na yung vertex. Dalawa na yung edge. So, palaki ng palaki yung T. Next step, choose a point na wala pa kay T, pero adjacent sa any of the vertices in T. For example, this point. Adjacent din siya kay V1. So, kukunin ko yung edge na to. Observe that adjacent din siya kay V sub 0. So, it's up to you kung aling point at aling edge yung gusto mong isama doon sa T mo. Pwede kahit alin. Basta kailangan yung new point, wala pa kay T. Tapos idadagdag mo yung edge na nagko-connect doon sa new point saka doon sa kung saan man siya adjacent na nakay T. Yan. Next step, pili ka ulit ng point na wala pa kay T pero adjacent to any of the vertices ni T. So for example, this point here, let's call this B4. So wala pa siya kay T pero adjacent siya either kay V1 tsaka kay V0. Sabihin natin, kunin natin yung adjacent na edge kay B4, B0. Yan. So, 3 pa din yan. And it still satisfy the conditions na wala tayong cycle na nabubuo. So, pili ka ulit ng new vertex na wala pa kay T. Kumbaga yung T, nadadagdagan ng nadadagdagan. Ha? So, after iteration, so at first iteration, kumbaga yung unang T natin, so lagay natin sa iteration 1, ito, iteration yung unang-una. Sa first pili, dalawa na sila. Yung pangatlawang pili ng vertex, tatlo na yung laman. V0, V1, V2. Tapos ang edges natin, may edges na tayo na V0, V1. Nandun din yung edges na V1, V2. Okay? At the next iteration, pinili na nating vertex set. So, lumalaki ng lumalaki yung T after each iteration. Madadagdag na yung V1, V2, V4. So, kumbaga, yung T4, yung 4T natin, is simply yung third T plus yung new edge natin. Yung edge na V1, so natin connect, V0, V4. Yan yung T4. So, dagdag lang ng dagdag. Since meron pang point na wala kay T, sasama natin yon. Basta connected to any. So, for example, this one. Connected siya kay, pwedeng nakakonect siya kay V2, kay V3, kay V0, or kay V4. For example, gusto kong connection niya kay V4. So, ano yung T5? So, T5 is simply yung T4 plus yung edge na B4, B5. And finally, this one, connected siya kay V4, kay V5, tsaka kay V1, tsaka kay V0. Pili ka lang ng kahit aling connection ang gusto mo. For example, gusto mo kay V4 connection. Okay. So, si T6 ay equal sa T5 plus yung edge na binuo mo. B4, B6. Okay? And right now, meron na tayong 1, 2, 3, 4, 5, 6 na edges. And all the vertices are included in our T. So this is another T. Right? So, pabaliktad naman yung ginawa natin. Instead of deleting, kasi nagde-delete tayo ng mga edges, this time, nagdadagdag naman tayo from first vertex. You have the freedom to choose kung anong initial vertex ang pipiliin mo, and you have the freedom to choose kung ano yung susunod na vertex na pipiliin mo. Okay? Basta kailangan, dagdag ka lang dagdag ng edge. So, ang nangyayari, nagdadagdag ka ng edge, pero iniiwasan mong makabuo ng cycle. Kasi once na bumuo ka ng cycle, hindi na siya tree. So, this is now a maximal tree na acyclic. So, maximal siya na acyclic. Maximal subgraph ni graph ni G that does not contain a cycle. Take note na once nagdagdag pa ako ng isa pang edge, for any edge for that matter, magkakabuo na ako ng cycle. So, yung kanina, maximal na. So, that maximal acyclic is now our spanning tree. Okay? So, dalawang way kung paano ka bumuo ng spanning tree. Either you create a minimally connected graph by deleting any edge that will remove the cycle pero will retain the connectedness of the graph. So, nagdi-delete tayo ng mga edge para mawala yung mga cycle, pero nananatili pa rin connected yung graph. So, nakitira pa rin tayo ng kalahat, nung kabilang side ng cycle. Ang tinatanggal natin, isang part lang ng cycle para connected pa rin siya. Or, pwede rin tayo magsimula into a particular vertex and then we try to connect it to the rest of the vertices, isa-isa, without creating any cycle. So, parehong ang nabubuo natin, nag-meet lang sila sa gitna, ay pareho pa rin walang cycle. So, as an acyclic, it's maximal. As a connected, it's a minimal subgraph. So, either a minimal connected subgraph or a maximal acyclic subgraph of the original connected graph will create your spanning tree.